Zen imaging software from Carl Zeiss provides a number of methods of quantifying image data. This tutorial is intended as a follow-up to the previous introductory walkthrough of the image analysis module and assumes the viewer is familiar with basic concepts of thresholding or segmentation, filtering, and reporting of data. Here we will extend those concepts by involving two fluorescent channels in a nested analysis, identifying individual cell nuclei and classifying them in groups based on the occurrence of the presence of mitochondria. The automated image analysis module is accessed under the Analysis tab in the window titled Image Analysis. Let's begin by creating a new analysis configuration and name it appropriately. I'm calling my configuration Cell Classifier. I begin to set up the configuration by clicking on Setup Image Analysis, and I rename the class's line as Image and rename the class line as Nuclei. However, the question I want to answer is how many mitochondrial fragments or events are found in each nucleus. So I'm going to need to look at the red channel. I don't want to look at all the mitochondria, however. The only mitochondrial staining that is valid is that which I can find within the nucleus, and so the mitochondria exist as a subclass of the nuclei. I click on Add Subclass and name this class Mitochondria. Notice that we have a subclass of mitochondria, but we also have another classes line. When we create a subclass, the original object that we have identified in the primary class becomes the field of analysis for the objects of the secondary class. For the primary class, the statistics of the entire image will be reported on the classes line, where for the subclass, each nucleus will be treated as an image or a field of its own, with field-level parameters such as object count relating to only the individual nucleus. For our purposes here, I will label the subclass field-level line as MitoCount, as we're going to be reporting mitochondrial object counts within the nucleus at this level. Skipping to step 3 of the wizard, I have chosen to use automatic thresholding on both the DAPI channel for nuclei and the Psi3 channel for mitochondria. The yellow mask identifies nuclei, with the green mask identifying mitochondria. Note that the only valid mitochondria are those that are found within the nuclei. Moving now to step 6 of the wizard, the subclass we have created is going to report the mitocount for each nucleus. Ideally, we would like to consolidate the results of the mitocount and the object-level properties of the primary class into a single table output, and we can do that. If we edit the mitocount results, we can copy the count results up to the object-level results from the primary class. Moving through to the results preview in step 7 of the wizard, we can now see how this looks. Selecting the nucleus results, I can see I'm reporting the area of each nucleus, but I also have the count from the subclass reported. This is the result I was looking for in my image analysis. Completing the configuration and running the image analysis of my full image provides me with data for the full field. I can view the data for the nuclei by clicking on the nucleus line of the results data, and I can see what we have just under 100 nuclei. I'll sort the data results table, just out of curiosity, by clicking on the header of the column that contains the mitochondrial event counts. Now I can easily see that I have 20 nuclei with no mitochondrial events. If I want to see a graphical representation of how many nuclei there are that have each of the possible numbers of mitochondrial events, I can do that easily through the graph on the right-hand side. Under the Custom Chart tab, I want to set the chart type to a histogram and the x-axis to represent the mitochondrial event count. If necessary, I can adjust the number of data points that's used to represent this histogram, but here we have a relatively small range from 0 to 28, and the histogram shows us the distribution nicely. Adjusting my display so that I can see the image nicely again, I can click on any one of the populations represented by the histogram, and each of the corresponding nuclei are highlighted in the image. This is a nice tool for doing a sanity check of your results, possibly investigating outliers of the distribution of bias in your image that can allow you to then return to the image analysis configuration and refine your parameters. Of course, as shown in the introductory tutorial, this data can now be easily exported by creating a table document and exporting a CSV file to open Excel. With that, we can conclude our walkthrough on using Zen for nested image analysis. Look for further tutorials on powerful tools within Zen Image Analysis, and until then, enjoy your time exploring Zen.